Good morning, everyone. Today is August 17th, 2019, and this is the John Chappell Natural Philosophy Society Science Chat, and I am your host, Franklin. So today we're just going to have an open chat, and the first topic was brought to me by Aberjex Chattervati. Sorry if I mispronounced your name. But he's got this question here. So everyone listen carefully and see what you think. So he says, suppose there is a bucket filled with water. There is a duck in water waves. Okay, we have a bucket and we have duck in it and he's in some wave. Now, bucket is pushed by some people. Then with respect to the other system in which the bucket is moving, the velocity of the water waves will be different from the velocity of the water waves with respect to the bucket. So among the wavelength and frequency of those water waves, which one varies from the frame of reference of the two systems, and which one is constant? Which one is constant from both frames of reference? Okay, well that seems like a tongue twister to me. So the physical situation, we have a bucket, it's got a duck in it, the duck is making some waves. So normally if the bucket was just stationary and the duck was in the middle of the bucket, we would just see these concentric waves go out, right? So that would be the stationary situation. So next we add in the situation that we stick the bucket on like a skateboard and we move it with some velocity. Now, so the question is, what is the wavelength of those water waves? And how does that vary? So I think that's the nature of the question. So I think, first of all, I'm going to have to eliminate any factors due to acceleration. So I'm going to presume that we're just comparing the bucket that is just stationary compared to, say, a second bucket which is moving next to it, I suppose, and then compare the waves from both of those. So I'm thinking, since the bucket itself forms a frame of reference, that the waves would pretty much look identical whether the bucket was stationary or moving. So if I put a camera on my bucket that's stationary and I put a camera on the bucket that's moving, I watch the duck in there doing his thing, I would imagine I would probably still see just a series of concentric rings, so that the picture from inside the moving versus the non-moving one, I think would probably be the same. And because of that, you could say that the frequency was unchanged, basically. But the question here, I guess, is, do you disagree with that? That basically the frequency.
I'm not disagreeing exactly. I'm not getting the correct conception. See, among wave velocity is a product of two factors, that is wavelength and frequency. If wave velocity is different from the frame of reference of the two systems, then among wavelength and frequency, which one is varying from the frame of reference of the two systems and which one is constant? That I am not getting.
Well, I'm saying that the way to understand this is like you put a camera and, that camera could have like a ruler on it or something along with the clock, I suppose. But I'm not sure this is true, but from my understanding of how this might work, that if you put the screen monitors side by side, and you looked at what's happening in moving and non-moving bucket, assuming that you have no idea which is which, you could not tell the difference between either one. Would you agree with that? That if I put a camera on the moving bucket and a camera on the stationary bucket, then I put the two screens side by side, that both of them would look like a duck, and you would have radiating concentric waves. That they would look identical. That it wouldn't matter that the bucket is moving. That the frequency that you would observe on the screen that you're measuring by your experiment would in fact be the same. That's kind of my contention.
Yes.
So James, you raised your flag. Do you have a comment on this?
Yeah, this sounds like a special relativity type of question or problem. And in this case, what you just described, I believe correctly, Franklin, is when the observer is in the same reference frame as the bucket and duck. If the observer were stationary and the bucket and duck were passing by, you'd see Doppler effects, I would think, along the vector of the motion of the bucket and duck compared to the position of the observer outside the bucket and duck in that reference frame. So that's all I wanted to say.
Yeah, I would probably conclude the same thing, that what you're looking at here, it would be from the reference frame of the stationary bucket. If you looked at the waves in the bucket that's moving, you would see the waves that are going forward would actually appear to be shorter to you. Now that's, as James says, is a Doppler effect. The same effect that if you have a train moving towards you, the sound is higher. You're going, yeah.
Yeah, I understand. That is the Doppler effect. I understand that partially.
So if you accept that, then so your question here, which is a little bit mind-bending here.
See, in the train example, you are saying the train is in motion, but the air in which the sound waves are being formed, the air is not in motion. But in this dark example, the thing is more complicated, because in dark example, the water in which the waves are being formed, that water is also moving. That means the medium in which the waves are being formed is also in motion. In the train example, you said the medium, that is the air, is stationary, but in the dark example, the water is in motion. That is, the medium is in motion. This is more complicated.
Yeah, I would agree that that's not the same situation as a train, since so the difference here is that you'd have to have the train, but it would actually have to be in its own box of air, I suppose. And
well, actually, I think it is the same situation, Abhishek. Your duck in the water is just simply, you can say, a sound generator. And just like the train makes a sound, what Franklin explained in terms of the arriving and receding train from an observer on the side of the tracks is correct. So I really don't understand what the issue is. And Abhishek, speak slower. Speak slower so we understand you. Thank you.
See, actually, Mr. Keen, I was saying that in the train example, the air, that is the medium in which the sound waves are being formed, that medium is stationary. But in this dark example, the water waves are formed in water. The water is not stationary, because if you push a bucket, the water moves along with the bucket. So if the medium in which the waves are not stationary, then if the medium is in motion, then can we say this is a Doppler effect?
well, in some ways, like I said, if you were an observer in the moving bucket, then you would not observe the Doppler effect. Would be the main thing. As a person who's in the frame of reference of the moving bucket, the frequency is not changing. versus the train situation where, well, let's see, is that true? If you were standing, yeah, I think if you were standing on the outside of the front of the train, I think you would still get the Doppler effect. It would just be a constant higher frequency for you, I think. Versus the you just hear the
Yes.
I would think. But in the case of the medium being constrained within the actual frame, then you would audibly hear the same frequency as you did before, as if you were stationary. Now the question is that, first of all, the wave isn't actually going to get past the bucket. Is the other thing, is that observationally, the person who's stationary is not going to be able to, at least if there were audio waves or something like that, because the waves don't actually penetrate into the stationary frame space. But I'm thinking that you could visually observe what's going on. So we could provide a third camera, which is taking a picture of the moving bucket as it goes by, and it can compare it against the rulers and clocks of the stationary the stationary frame. So we have to figure out what would that look like. So I'm thinking that the moving bucket, it has, like, let's say there's like, it's got enough space to fit, say, 10 waves into it. And when you start taking that frame and you start moving it forward, then more of the waves will be able to pass by any stationary point. There will be more wave crests moving past the stationary point, I think.
Yes.
So I'm thinking that, let's see, I'm just thinking on my feet here, that if you were to just sit there and observe, so the frequency is like wave crests per second passing any fixed point is what we would have to be doing. So so I'm just doing like a mind experiment here. I guess Einstein would call it, thought experiment, that we kind of have to set this up in our minds and see what happens, because I don't know, it could be something strange happen, but in my mind, I'm thinking that since you could still count the waves and it would just be coming faster, that I still think that the Doppler effect would still apply, and it actually technically doesn't matter that the waves are just constrained within the bucket. What's important is the observation of the number of waves that will pass by the stationary observer's viewpoint, I'm thinking. And that would still remain unchanged in that situation. So that's kind of how I see it. Not unless you disagree. That could be wrong, but without having an actual bucket, and I was thinking I'd have to draw a picture to really convince myself. So James, did you have a comment on that?
Yeah, I think the third reference frame that you mentioned is really the same as the second, except that you basically have to calculate some differences due to the different position of your third camera. I think there are really only two relevant reference frames here: on the train and off the train, or standing by the train track. And it's really special relativity 101. I still don't understand what Abhishek's question actually is here.
Well, I think it has to do with the change in the physical setup. So Usually we consider the Doppler effect as the train and the stationary observer all immersed in the same medium. I guess a frame of reference, I suppose. But in the case that he's putting up here, the thing that's moving is bringing along its own frame of reference, right? So if the equivalent would be
it's if I may, if there is no acceleration, as Franklin stated at the beginning to explain his outlook, you just basically have what's called an inertial frame, and it's moving at said velocity, and the waves are going to be spherical in that inertial frame. The observer by the bucket or train, watching it whiz by, is again going to be a different frame, and you're going to then get the Doppler effects. But that's all I have to say on that.
Well, I think this situation would be
There
more.
There are only two frames, in other words.
Yes, I think what this situation would be like if you were a passenger in the train, right? If you're a passenger in the train and the train is moving 70 miles an hour, the air in your train is moving at 70 miles an hour, right? So the question is, from the observational standpoint of the person who's sitting on stationary, as a train comes whizzing by, what are you going to observe about the wavelength and frequencies of something that's, say, making a sound? So you have a speaker, it's putting out like a 440 hertz tone or something, and there's the guy on the inside of the train. Both of those people hear exactly 440 hertz. It doesn't matter how fast the train is going. Now, like I said, the person who's standing on the ground is not really going to be able to hear the tone that's coming from inside the train, because the two mediums are disconnected, right? Of course, all of this is presuming that there is a medium, which is a kind of a question when it comes to real space. But since we're talking about real waves in either water or air, then I'm pretty sure we can barely confidently say that we're actually talking about a physical medium with particles and such, right? So what do you think of that situation where you have you're comparing the situation of a passenger inside the train with a tone generator versus a person outside the train sitting on the ground with the same tone generator? You think there's a difference? Now, I'm thinking that you'd have to have the guy from the outside would still have to have some way of observing what he perceives as the tone. I'm not exactly sure how you could do that. I was thinking, like, photographically, you could figure out where the peaks were. But that those peaks would still be compressed by the motion of the train to the observer on the ground. So I'm thinking that that's my answer to the question. That it doesn't really make a difference. What do other people think? Maybe Bob, maybe you have some comments. Do you think it would remain unchanged as far as observation of Doppler effects go?
I think you're right. It's a Doppler effect. That's all.
So, Abhishek, what do you think of that? I think the group is kind of concluding that while it is a physically different setup than just straight Doppler, that the Doppler effect would still be observable, I think, is the bottom line.
Yes, Doppler effect is still observable, but it is not only the Doppler effect, but because if the medium in which the waves are formed is in motion, then can we say that it is a Doppler effect?
Well,
the
so
medium
are
is not
agreeing or disagreeing?
See, if the source or motion are in motion and the medium is stationary, we can say it is a Doppler effect. But if the medium is also in motion, then can we say this is a Doppler effect?
Yes, I think that's what we're concluding. That the interesting part is that from within the bucket that's moving, they would not observe any Doppler effect, which is different than the just a wide open situation where you have the duck just making a wave in just the open air. But the Doppler effect is due to actually the crests of the wave arriving sooner. And observationally, I think you could still see that effect that the waves are arriving sooner at any given spot. But I'm thinking that now the complication here is that as you will see the duck go by, I can see that the waves would be compressed, but as the duck goes by, I would think that the waves would still be compressed as they go by. So you would just observe just a constant higher frequency as the duck goes by. So it wouldn't be like it would just be the whole time, I think. So maybe that would be the difference.
Yes.
I'm kind of.
But wave among.
Like you have a ruler, and this is like the. Like 10 beats per second or something like that, right? And then you count, and if I keep it still, it's 10 beats, but if I go move it faster, that might be 20 beats per second, right? If I move that ruler that way. And since the waves are uniform in both sides of the duck, right? That you'd see a Doppler effect, but you wouldn't observe as it moves away any difference in frequency, maybe. So maybe there's a difference there.
Frequency is constant, wavelength is varying.
Now, did you have a particular opinion on this yourself? Is there because I'm this is like the first time I'm really seeing it and really trying to seriously analyze what's going on here. I was wondering, do you have a preferred explanation for what happens here?
Yeah, I was reading Dr. Glenn Borch's book, Infinite Universe Theory. In that book, the Doppler effect has been explained. I read the book Infinite Universe Theory by Dr. Glenn Borch. They say that in that book, in the beginning also and in the end also, the Doppler effect has been explained. Shall I give you the link of the blog?
Yeah, if you could type that into the chat. So
okay,
did this question come from that blog?
See.
Yeah, go ahead and type that in if you can. Let's see.
Yeah, I'm giving you the link of the blog. It contains the Doppler effect.
So he explains the Doppler effect but I would think that the Doppler effect it doesn't require a whole lot of explanation. I suppose it seems kind of simple. But let's take a look at here and see if it's more complicated. Let me share the screen here.
While you're looking that up, the comment by Franklin that you could possibly get the same tone when you're in a reference frame different than the inertial frame of a sound generator passing by, having a constant tone I don't think has ever been observed, number one, and number two is contrary to the math of special relativity.
Well, you got to think of if you have the ability to observe the frequency that's coming out of the moving train, then maybe that would be the case.
And what is the real meaning of this one cycle of a wave? That is it the displacement caused by one cycle, displacement, or is it the length of one cycle?
So let's see. It looks like this is Glenn Borchett's website, isn't it? And so
Give me the link. Right.
So he's explaining the standard, and you've asked the standard question about Doppler, and he's explaining the standard answer to Doppler.
Oh, here.
And this is the standard picture of Doppler, but the situation that you're describing, it wouldn't really look like this. Like I said, if you were to put a camera on your duck, I would think you just see a perfectly concentric situation. So I think he has adequately explained the normal Doppler effect. But your question goes beyond that and says that if you actually have a bucket moving, then
Yes,
what do you...
See, I have one question. Even if the train is making sound waves here on Earth with respect to the solar system, then the Earth is also in motion. Then with respect to the solar system, then the same thing will happen which is happening with the duck in the bucket. With respect to the outer system in which the...
So James, what do you think? So this is like the standard picture of Doppler. You can see that the leading waves are compressed compared to the trailing waves. But the situation that Evercheck is describing is that if you were to put a camera on the moving bucket, you would just see a concentric set of waves. You would not see this compression happening.
Well,
So
exactly. That's the inertial frame of the bucket.
Yes, with an inertial frame of the bucket. Within the
You're
inertial
in the frame of the, and that's called an inertial frame.
Yes, and within that inertial frame, you would not observe Doppler effect.
Exactly. Yeah, that's special relativity.
The question is, if there's no Doppler effect inside the bucket, would there be Doppler effect outside the bucket that's observable to the stationary reference frame?
In other words, if you're moving with the bucket.
No, if you're not moving with the bucket, but you're looking at that are in moving, what observe?
If you're not moving with the bucket, you're in a different inertial frame. And so the Doppler effect would apply. So there's only two options here. You're in the frame of the bucket or you're not. If you're in a different frame and the bucket's frame is moving with reference to you at a constant velocity, there is going to be Doppler effects.
Yeah, but what kind of Doppler effects? So we're talking about you're observing from the stationary frame. You're looking into the moving frame. Within the moving frame, you just there's no Doppler effect going on within the moving frame. So the question is, are you going to observe Doppler effect outside? Because inside the frame of reference of the bucket, you're not seeing this picture with the compressed waves. You're not seeing that at all. But this is used to explain the Doppler effect when you have an independent source moving within the stationary frame, which we can understand, right? That pushes because you're moving physically through the medium at some velocity. But in this case, the velocity through the medium in the moving reference frame is 0. So you would not see any picture anywhere in the entire universe that looks like this one. Because it would not be any actual compression of the waves. But I'm saying that instead of this picture, you would just have a picture of uniform concentric waves heading out from the middle. So every one of those peaks is going to be in exactly the same place. But as those peaks, if you can observe from a stationary standpoint where those peaks are, you just painted them with a brush or whatever. You took a picture, you painted with a brush, and you observe them zipping by you. then that would just be a series of wave crests zipping by you. It would be at a higher frequency because they're moving, but you would observe it to be the same frequency the whole time.
Well, you have to add, I believe, the geometry. If you're moving through the medium, you're in a different reference frame than the sound generator itself. So again, there's only two options. You're in the frame of the sound generator or you're not.
Yeah, and the question here...
There's only two inertial frames, the one of the sound generator and the one of the observer.
Well, that's obvious. That's obvious.
In the same frame, or he's not in the same frame, he's in a different inertial frame. There's not a third option there, I don't believe.
That's not relevant to the question. That's just an obvious observation. The question is, what does the person who is stationary observe?
Well, that person then is in a different inertial frame than the sound generator, and he's going to observe the effect.
So what? I don't care about he's in a different frame. I only want to know, what is he going to observe?
He's going to observe changing sound frequencies as the object approaches and recedes in its inertial frame.
But I would assert from what I'm doing,
as the data shows, by the way.
You would not observe, I mean, if there was a window that they could take a look at the bucket as it goes by, that you would observe, my contention would be that you would observe exactly the same frequency from the time it enters your purview to the time it exits. So that's what I think.
Again, as I mentioned, I don't believe anyone has ever observed that in any experimental setup whatsoever. And
because it hasn't been done.
If you're observing the media generating the sound or the frequency go by you, well, you're in a different inertial frame. You can dress it up in words and pictures any way you want. But if you're not in the inertial frame of the media generating the sound or the frequency, and that inertial frame is moving along past you, then you're in a second inertial frame. And the Doppler effect would apply. So what you're talking about is a third possibility that no one has ever observed and is contrary to the mathematics of special relativity. I'm not here to defend that mathematics because they have to be revised in terms of binary mechanics, or at least cast in terms of the concepts of binary mechanics, which is another topic.
That's why Avertech brings up this question. I mean, maybe it is. I mean, I hadn't thought about that really, and I hadn't really thought about the particular...
Well, has anybody ever observed that in the history of Earth?
The question is, has anyone tried? I believe that if you did try and do this experiment, that's exactly what you would actually observe. In my mind, doing the thought experiment, that is what I observe. I would observe a constant higher frequency as the bucket goes past. I would measure one frequency, it's higher.
But why does frequency increase when the bucket is fast? And if frequency is changing, will the wavelength remain constant?
You would observe a higher frequency because you would see more crests going past a fixed point in from the bucket going by. I mean, I think I'd have to draw this exactly, but if you had a wave that was moving, say, 10 beats per second, something like that, so it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you're stationary, you would see those 1, 2, 3, 4, 5, 6, 7, 8, 10 go by, right? Now suppose that, so the length could be like that or something like that. So the thing is, if you were going twice as fast as a stationary frame, if you carried a frame like that, then that means that you could fit 20 of those beats could fly by you because it's moving in the same amount of time. So that would, for you, looking at it, would observe to be a frequency twice as high. I would think.
Yeah, I'm reading a line from Stephen Brand's book named Disruptive. It is about Doppler effect. The Doppler effect, also called the Doppler shift, defines mathematical equations that explain the apparent change in wavelength resulting from the motion of the source, the receiver, or the transmission medium, or a combination of the three. This is the sentence written in Stephen Brand's book named Disruptive. That means it says that Doppler effect can be because of the motion of the source, it can be because of the receiver, and also because of the transmission medium. That means Stephen Brand says that if the transmission...
You're going to have to speak a lot slower if you want us to understand you, okay? Speak
I'm reading the line.
as slow as I am, okay?
Okay, I'm rereading the sentence. The Doppler effect, also called the Doppler shift, defines mathematical equations that explain the apparent change in wavelength resulting from the motion of the source, the receiver, the transmission medium, or a combination of the three. This is what I found in Stephen Brand's book named Disruptive. Means it is Doppler effect is not only because of motion of source or receiver, it is also because of the transmission medium. Because that means if the transmission medium is in motion, then that can also cause a Doppler effect.
Well,
Hello?
that Doppler effect, though, presumes that, you know, you're not in the situation you describe where you have a bucket which is carrying its medium along with it. So, this is like the passenger in the train. Passenger in the train observes no Doppler effect. Now, if the waves were able to penetrate the train and go outside and be heard by somebody, then you would observe a Doppler effect. They would observe a Doppler effect, and there would actually be a physical compression of the waves. But in the situation that you're a passenger in the train, the waves themselves aren't experiencing any kind of actual compression. So
Right?
the question, so I don't think that the Doppler effect really technically applies. I mean, it's not observable, actually, is one problem.
Yes, that is not observed by because speed of sound or light is very high compared to our day-to-day speed. Like speed of sound or light, because sound travels at 343 meters per second and light travels at 299,792,458 meters per second. All these high speeds are very our normal day-to-day speeds are almost negligible compared to all these high speeds. That's why we don't observe them in our day-to-day life.
Well, I'm not sure I understood anything you said there. Once again, you're talking way too fast for us to understand what you're saying.
I said that, see, the speed of sound is 343 meters per second and speed of light is 299,792,458 meters per second. All these speeds are very high compared to our day-to-day speed. That's why in our day-to-day life we do not observe Doppler effect of sound or light. Because a train also cannot normally does not approach the speed of sound. Hello?
Well, once again, I don't really understand what you're saying there. But so what do you think? I mean, I can only give you my opinion. So, and my opinion seems to differ a little bit from James. That in the situation you describe, presuming that you could observe the wave, just the peaks of the waves. I mean, you can think of it if you were in a train and you measured the peaks of the waves, and on the window you physically dots where those peaks are.
Yes.
From your sound generator, you know, that's the frequency. Maybe it would be like 2 inches apart, right? So you have this series of dots painted on the train. So therefore, you set up a camera that will read those dots as they come by. And you can see that the frequency would increase as the train gets faster and faster. But you would observe only a single frequency. As the train goes by, you'd like, you know, it would be there and gone.
Okay,
And
Franklin.
Yes, that is also, that I know, because actual frequency is unchanged. Dr. Dane Borcher has said this to me, that actual frequency is unchanged, only the apparent frequency changes, and wavelength is the one is actually changing in the Doppler effect. But
Okay, what Franklin has just said, if I may quickly interject, in one sentence he included two frames, and suddenly concluded that you'd hear a constant sound with no Doppler effect. The first frame is that you're on the train where the sound generator or wave generator is. And then in the same sentence he says, but if you could observe it moving past you, then you'd get the same sound. No, you'd get the Doppler effect. If you're on the train, it's the same sound. If you're off the train,
yes,
it's a Doppler
yes,
effect. There are only two
yes,
alternatives here.
yes, I know that.
Well, then what really
no,
is?
I would disagree.
I have
don't believe
no
the
idea
Doppler
what your
effect
question
applies
actually
here.
is then.
The Doppler effect would just basically not apply here. It could only be done if you could just observe. You would have to do a translation to figure out what the frequency appears to be. The only way you could do that by painting dots on the outside of the train so you can see where the wave crests are. And when you observe those dots and not the actual, there's no actual frequency penetrating the train here. So there's nothing that can be actually compressed. But you can observe the wave crests going by. And those would be going on at constant speed according to the velocity of the train.
Yes.
Perhaps what Franklin and Abhishek is saying is, what about the frame where you're on the train, but you're moving with reference to the sound generator on the train? Then you'd get a constant tone in that case, because you're basically...
Well, that's not what I'm talking about. What I'm talking about is actually the Doppler effect does not apply here, because in order to get the Doppler effect, you actually have to be moving at velocity through the medium, whatever it might be. That's not what's happening here. That's not the Doppler effect.
I agree with what Franklin is explaining. Now, if you had a train and the windows were open, then you have a different situation. But with the windows closed and the sound can't actually come out of it, and there's some way that Franklin is saying you could actually observe the waves inside the train, inside the glass, without actually hearing them. What he's describing is how it would be.
Yeah, so what do you think about that, James? It's not, you can't have a Doppler effect if the object is not moving at speed relative to the medium. I mean, that's an interesting point that can't happen. Physically, it can't happen, I guess. I suppose I'm trying to think of some situation you might do this in some space between two spaceships. Vacuum. We're not talking about actual air, but then maybe talk about light frequencies or something.
Yes.
Something like that. Oh, you're muted, James.
I'm muted.
You're muted there. So go ahead.
Okay, now I'm unmuted. If you're in the inertial frame of the sound generator, you're going to hear the constant tone. If you're not in the inertial frame of the sound generator, whether you're inside or outside the train, doesn't matter. If you're moving, let's say you're running down the long train car, but the sound generator is stationary somewhere in the train car, there's going to be some very small, because you can't run very fast, some very, very small Doppler effect, because you're in a different inertial frame than the sound generator. So again, there's only two options here. You're either in the inertial frame of the sound generator or observing the sound generated from a different inertial frame.
Yes.
But once again, the real question here is, what would the stationary person observe?
Think of it this way. It might be easier. You have water waves or water inside the train, halfway up the window height, and you have a stone or something being dropped inside the train as it's moving along, which is causing ripples in the water, and they can be observed from an outside observer because the water height is halfway up the windows. You can see the ripples of the wave along the train as it's moving. Certainly, as it's passing an outside observer, they can count how many ripples they see on the windows as the train goes by. They're also sitting in water outside the train. The same thing is happening in the water outside the train with its own rocks being dropped, and then you can see the ripples. You count a different number of ripples passing you, the ones that are outside with you in the water where you are, and the ones inside the water as the train goes by. You would see a difference in the rate as the ripples passed you for those two situations. But since the windows are closed in the train, they do not mix with the waves outside or the water outside the train. They're like two separate environments. If you opened the windows and allowed the water to mix, then you have an entirely different situation.
Yeah, actually, you didn't come for the initial question that Averchek had asked, which is exactly that same situation, except he said you have a bucket and you put a duck in it, and you're trying to observe. But I think that that the train analogy, yeah, that's brilliant. So you can kind of see that from an observational standpoint, you could easily see the higher frequency, I think.
Yes. Without it affecting you.
Any actual Doppler, it wouldn't matter what your position was relative. I mean, if the train was infinitely long and, there was just a wave generator and they're generating a constant wave all the way from one end of the infinite train to the other, you just see a higher frequency go by you the whole time. But it have to be measured at a particular point, right?
Well, you as the stationary observer outside the train, that's your point, basically.
Yeah, so Abhishek, I think that would be our conclusion here for you. So you have some other analogy, like the train with the waves that you can visibly see go by you, and that could be like an infinitely long train, and it would just be a matter that the frequency would be increased relative to the speed of the train, I would think, if you were to observe it that way. But because the two mediums do not intermix, then I don't believe that any true Doppler effect could be possible.
Yes.
All right, so that will conclude, I think, that very interesting question. Initially, I didn't think it would be that interesting, but I think we may have made some interesting conclusions, and someone could actually see whether they can do this experiment. I don't think it'd be that difficult, and get that result, I guess. So that's how science is done. We set up a question, sets up a hypothesis. We think of what would happen, and then we could do an experiment to confirm what might actually happen. So that's interesting. So thank you for bringing us that question. So the second topic, James sent me a reply to a message I had sent. So me and James, we have kind of some similar ideas about how the entire world could be actually implemented on, say, digital hardware, basically. This is, in the mainstream, kind of called simulation hypothesis here. So, so James has some comments here, so I'm just going to go through this, and I'm going to just, I did not get a chance to reply to them in email. And I seem to be, for a guy who doesn't have that much else to do, I have to be awfully busy. But I appreciate James's the time he took to read my paper. So my paper is called, the God Computer, basically. And so the first comment here is that, it's the idea that we are embedded in a simulation is discussed in many places. And you said that someone needs to write a review paper tracing development of the idea so that newcomers can learn how the idea was developed, who contributed, and who formulated it, etc. Yeah, I'm not exactly sure who came up with this idea, but simulation theory actually seems to have gained some traction. I mean, you can go to entire conferences actually devoted to this topic. So it's not just you and me, James. There are a lot of other people who think that might be the case. In fact, let's just do a little searching here on the internet. Let's see.
Agreed. Agreed. I'm seeing this idea all over the place, and since I haven't systematically studied it, as perhaps you have, in more detail, I thought a review paper on the subject would be interesting, so we could trace its development of this idea, at least for my benefit.
Well, I always go to the source of the ultimate source of knowledge, which is Wikipedia. So if anybody knows, it would be Wikipedia. Okay, and if it's on the internet, it's got to be true. So it have the origins here. What do they say the origins is? There's a long philosophical history.
Hey,
Back
James.
to antiquity, back to the Indians, back to the Mayas.
James, Bob Gray.
Hi, Bob.
How is your theory related to bit string physics?
I've never heard of bit string physics, so I can't comment. Right, I'd have to look it up.
Yeah, look it up on Wikipedia. Yeah.
Okay, I'll do that. I'll make a note of that. Bit string physics.
Bit string physics. I haven't heard that myself either. Testing the hypothesis physically. Let's see, how did they propose to do this? Simulation, blah, 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 which reached, they had a Kickstarter. It generated $236,000 to test this? That's a good way to make money. But I would think the ultimate way to test the simulation hypothesis would be to come up with a physical experiment that proves that all states ultimately degenerate down into a binary state, right? Just a 1 or a 0. And if that could be shown, then that would certainly indicate that there is some binary basis for the universe. So ultimately, if you were a sentient being inside of, say, my computer, you would have to do some experiment to say that ultimately everything that's observed in the computer world ultimately had to do with a 0 and a 1. And that we have certain, you would observe the most quantization effects, I believe, are a direct observation of that binary nature, that perhaps you would find that time is quantized, just like in a computer, the time would have to be in quantum units. And you would find that space itself would have to be in quantum units, that anything that you could observe could not be observed to move in anything other than integer units. The quantization of space and time kind of would support the simulation hypothesis. But
that's the basic premise of binary mechanics. Now, computer games can be paused. Like 3D action, thriller, shooter games, and so forth, can be paused.
That's
there
right.
You go. Unpause it, and you're back in action. It's basically a computer program processing data.
Yeah, I've sometimes speculated that if that were true, that you could do some time travel kind of things. That if you could, you save the program, you save the current state to disk, and then you play the game, and then you get killed, and then you would effectively travel back in time by reloading your saved image. So that way you could travel back in time, right? That would be time travel, wouldn't it?
Interesting. Well, of course, if you're embedded in the game, you can't do that, and we're embedded in this binary universe.
Well,
So
sure
we
you
can't
could.
do it. As a matter of fact, if someone stopped the clock, paused the whole universe, and then started it up at some arbitrary time later, we, as embedded entities in that binary universe, would never know the clock was stopped. We'd have no way to know that.
Yeah, that's right. Time only has relevance to the things which are inside that environment. So that kind of gives you, I think, a more basic physical idea of what time might be. I mean, if we're a simulation, then time is just the number of clicks going by in the clock.
The programmer who writes the computer 3D game is like the god, and the player too, who can pause the game. So there we can move up. The players of 3D action games can move up to be the god, and can stop the clock or start it. But we, as embedded objects within the binary universe, can't do that. We'd have no way to know if the clock was even speeded up or slowed down, much less stopped. How would we know?
No, we wouldn't. But kind of getting back, that reminds me of the time travel paradigm. So, the other thing you would have to do other than resetting the state of the game, your player within the game would have to retain the memories of the at the time that you had decided to go back, right? Because if you were to go back in time and just restored yourself and you never knew about the future time, then what would be the point of that? Now, the point in time travel is know that you have traveled back in time. So as the creator of the game, you would have to be able to separately save your cloud memory at any given point in time, and then when you restore the game, to put the memory back to that player so that they know that they've traveled back in time, right? That would be the other thing that you would have to do in order to make this work effectively.
If I
then
may,
you could go and change what the future was.
If I may, in the paper on I forget the name of the paper now, but there's several paragraphs which pretty much show that travel backwards in time, or forwards for that matter, but backwards, so that's what we're talking about now, is impossible. And I might indicate that a big flaw in Feynman type diagrams is they show things going backward in time, which is mathematically impossible. So the whole foundation of Feynman diagram depiction of physical events is blown out of the water.
Well,
in other words, there's not T, what's called in physics, T invariance. There's simply not T invariance.
I would say in an absolute sense that you cannot travel back in time, that what's been done is done. But if we allow simulation hypothesis, then we can go and we can rewind just the state. If you can rewind just the state, then, I mean, you haven't traveled back in time. All you've done is you've taken some new actions to restore back the state of the world at some previous time, and then you run it forward. So technically, it's not actual time travel, because in order to go back in time, you'd have to reverse everything that happens everywhere. And I just And I think that just happened, and that what's what happened, it's done. It's a time only in the sense that you're in a state, really, but you haven't actually done anything, literally traveling back in time. So just that, so you can do exactly like reversing time inside a fixed box, like our universe and simulation technology, but not actually travel back in time. A little bit technical there. So let's go on. So your second paragraph says, if you plan to pursue this, consider writing a simulation program based on your cubic lattice and the rules for time development. If that were done, as with my simulation, your space quantization and time evolution rules should be able to duplicate any physical effect, including actual demonstration of light speed, as I showed in the conference, etc. And yeah, as a computer programmer, I suppose I should do that. But considering I didn't even have time to reply to your mail message at the time I got it, which was a few weeks ago, yeah, that's a good problem. I really got to sit down and do something.
Suggestion, Franklin. If you want to, I think you might be able in that browser magnify the text there. There must be a menu that drops down where you can zoom in on the text so it's more readable.
Yeah, you're having difficulties seeing that? Yeah, let's do that. Let's see, where's the menu here? The zoom. Yes, we need to do something here. There we go. How's that? That should be better.
Yeah, just keep zooming until it's real big.
Isn't that big enough for you? Okay.
Well, you could have the margins. What I do when I'm making videos is I have the margins of the text fill the whole screen. Oh, there you go. Now, okay, bingo.
Yeah, there. Okay. My screen over there. Mail. I can't really get rid of all the margins here. But yes, I would probably. I mean, it's actually the whole program to do your simulation there, and you show some results from that. But yeah, if I ever get the time, I don't know. So 3, that is the specifics can directly compete with my specifics. And mine are based on relativistic Dirac equations. In future work, if some known phenomena can't be demonstrated with my simulator, then something is wrong. Something perhaps like the bit operations detail needs tweaking, for example. All you or I can do is keep showing we can duplicate nature, e.g., I'd like to see your simulator make higher Z nuclei for BMLS showing light speed and deriving its value through simulation is what is stated in the physical constant derivation tree was a major difference. Let's see here. Then you have some differences here. So yeah, right now, if you have simulations and I don't, then that's one in the home for you and one in the big X for me. But I'm still considering actually still how you're getting the Coulomb force law to work. Like that's kind of a specialty of what I would say is the physical aspects of my theory. Because I think getting the positron and the electron to work such that if you get two in space, they'll spontaneously accelerate towards each other is one of the most difficult questions. So in my simulation theories, I am saying that you have the ones and zeros, and effectively it puts the wave are represented as like either on or off, kind of, or either it's expanding or compressing or something like that. In some way, there has to be some kind of wave emanating out of the electron. And so in my paper, I show like there's a square and simulated the wave. I'm not 100% sure exactly what the nature of that wave is. And we'll go into some more questions about what exactly is the nature of the box that's of the elements there. But that's still kind of an open question to you, because I'm not sure I still understand how that worked from your presentation. How do you get the actual attraction happening in your system?
Attraction between plus and minus, you mean?
Yeah, positron, electron. That's the simplest possible case. What causes those two to come together?
Well,
in your
I have a paper. I don't know the exact title, but it's in the last, say, 6 months on proton and electron motion in an electric field, both positive and negatively, and I show all the permutations. If you, let's say, in the upper half of a simulated volume, put added negative charges, the protons will be attracted to it, and the electrons will be repelled to it. Why?
What in
By
your program?
the action of the scalar bit force, or a bit operation, which tends to separate charge like charges.
So that's a postulate, though, in your system, right? That you have.
That's a postulate
bit forces
derived from the Dirac spinner, the relativistic Dirac spinner equation. So we run the simulator and do various experiments, and we say, do the positively and negatively charged bits, which are of the M type, which have a charge property, do they move in the direction that we know in classical physics they should be moving? And they do.
But that's basically saying
it's
charge.
that simple.
It has charge because it has charge. You're saying that
that's a postulate. Yes, the M-type bits by postulate derived again from the Dirac equation actually have plus and minus charge. Now the L-type bits, the second and only other type bit,
this is the
L-type
problem.
bit are magnetic monopoles.
Is that you have charge as a postulate.
Yes.
Now in my system, I don't have charge as a postulate. Charge actually does not exist as a fundamental quantity. That in my system, what I try to do in my simulations is I firmly establish the existence of a particle within the system. And then I use Newtonian mechanics to say that the only reason why a positron and electron should head towards each other is because they're being hit by, they're being impacted by some other particle on the outside. Similarly, if you have two electrons, those things are repelling each other fundamentally because there are actual particles hitting the electrons, pushing them apart.
Okay,
So
that's Max. My take on that is that's the classical interpretation of particle interactions, where they're explained by exchange of other particles called bosons. In this case, it would be photons in what you just said. And that's the classical approach to understanding forces. In binary mechanics, the forces are based upon the 3 different bit operations.
Yeah, so that would be a difference there. So, but let's see. We're starting to get into the differences here. So, let's see. So, you said my approach is binary. Yours is tri-state. That is, each spatial locus can have 3 states, 1, 0, or -1. This suggests to me that your approach is too complicated as a fundamental system state representation. Notice that ordinary workhorse computers use binary logic, not tri-state. Clearly, computers have decided it is more cost-effective to build binary computers than use tri-state logic. So first I would comment that I don't know, like you mentioned, I don't mention that it has 3 states. So I have still no idea where you would get that idea that there are three. So why did you think there were three?
Well, I read your God paper, your God computer paper, and it states that in there, unless I misread it.
No, there's nothing in there that says anything about tri-state. So that's kind of where did you get?
So in other words, you have in one spatial cube, in our spatial lattice of cubes, two possible types of bits that can be put in there. Yes or no?
Well, I would have to say that in some ways I want it to be only one or two. Let me bring up my paper here so we can.
Well, if it's two, and there's the possibility of having zero, that's tri-state. And if you could have more than two, my God, you've got a complicated system there. That's not even close to the beauty and simplicity of a binary system. You see, like when we decided here to quantize space, time, and energy, every decision was, well, what is the simplest option? If I have a cube of space, if we say that space is quantized, well, we're going to have a length constant. We're going to have to figure out eventually what that length constant is in meters. That's a fundamental, primary, our first principle, okay? And then we get our cube, and we have to decide what's the simplest thing we could put in that cube? Well, a 0 or a 1, period. You can't have two 1 bits in there, only one. And the state of that bit can be in a particular cube of space is either 0 or 1. Those are the only two options. If you say anything more than that, you're making it more complicated. I don't think the universe was designed with complicated ideas. It was based upon simplicity. And that's sort of missing in physics. That's sort of gone. I admit that parsimony, Occam's razor, ideas like that are passé now in physics. The physicists today will publish in Phys Review, our data don't match the theory, but if we add another term to the equation, then it does. Making their model more complex. Well, that's not the way binary mechanics goes. Show me anywhere in binary mechanics where something is more complicated than what it needs to be.
Let's see here. Where's my share screen here?
So
Okay.
if you've got two kinds of bits in there, Franklin, in a cube, including the 0 bit, well, that's tri-state.
Well, here I have my picture here. So
It's not binary.
Well, it might not be, actually, although I'm not sure if that is necessarily a problem. There would be mark coding around each bit. Say in a digital computer, I mean, literally, the only thing that thing physically knows how to hold is the 1 or the 0. But we could make a more complex computer that's say used for those physical bits to represent a more complex state. But ultimately, every cell would still be a cell. It just could represent possibly, if you have 4 bits per cell, that could represent like 16 possible things, I suppose.
Yeah, but computer makers don't do that, and I think the God, whoever that is, that made the universe doesn't do that. They go for the simplest option, because remember, to make your universe, you got to hire a contractor to do it.
Well, I think what God did was that he just invented the electron, and then once you had that, then everything else falls out of that. So in that way, I think God invented the universe with the electron, which is run by about 10 lines of code, and then everything else runs off of that. So in my case, but in case going back to whether there's a tri-state or a binary state, I mean, I would say, and looking at my pictures here, so I'm saying either the state is either on or off. So in this picture I have here, I have the electron spreading to take up 3 points here. Let's see here. Now, what did I say here? It's either cube representing 0, black cube representing the -1.
There's the -1. I read it. That's Franklin.
The -1 value spread left and right. So it's 0 or -1. Now the question is, do I have a +1 value? I don't think I do.
So what's the difference in the state between your black black location and the 2 gray locations? What's that?
What I do say is that in order to create pressure waves, I actually have to represent a value of 2. So the values that I at least have in my paper are 0, 1, and 2. So in that way, yes, I would have to say, yes, my blocks can have...
That's tri-state, isn't it?
Pressure differential.
That maps 1-to-1 to tri-state, mathematically.
Okay, well then I would agree with you then that it is tri-state then, because I've got at least 3 values, 0, 1, and 2 mentioned in my paper. So yes, I would agree, yes. But it may be worse than that, because in order to get the
proton, yeah, that's what I was interested in.
That I need
all kinds of things up there.
That the problem is that you have like 3 electrons kind of in the same place.
Wait a minute. Please help me. Kind of in the same place. You mean in the same cubic volume?
Yeah, there's 3 electrons right next to each other.
Well, now you've got 3 objects within one cubic cell.
No, I'm gonna just say 3 next to each other. Okay, you got quantized space. You got 3 electrons right next to each other. The observed electric field needs to be 3 times as much. You see, now the only way that can happen is if if each cell has a property. It may be called pressure. And that could have a number of values, say 1 to 256, I suppose. So in that way, yes. So in that way, it would actually be more than tri-state. That the pressure value is actually a separate property on the cell unit. So in my case, my thing is definitely more complicated. And I would agree that in my system, that in each cell, you would at least have a property called pressure, such that if you had like 3 electrons in a row and you observe the pressure like 5 units away, you would see that pressure value is 3 times higher than if there was only 1 electron present, because that's a property that you do need to account for, which is the strength of the electric field at distance. And I don't believe that can be done without having some kind of variable property in your space matrix. So I guess that's
okay.
I guess
well, in binary mechanics, if I may interject, sir, is this in the scalar bit operation, if 2 like charge m bits, say they're both negative charge property, are adjacent to each other, the scalar bit operation will tend to separate charge. This effect, when applied throughout a volume, creates separation of charge, which communicates to more distant sites at the speed of light, and that can affect distant charges, as shown experimentally by running different simulations, creating electric fields and observing the motion in the entire volume of plus and minus charges with reference to those electric fields that are added in the simulation. You add an electric field just by adding more plus or minus m bits on one side, or wherever you want within the simulated volume, and then you run it and see what happens.
But how do you explain the situation I did which is the difference between having 3 electrons and the field that's produced by that versus a single electron at distance. So how do you explain?
Well, you're
3
postulating
electrons
again something else that you have to explain that other than an elementary bit operation, which is my only postulate there. And so far, it explains particle motion in
Well, you haven't explained to
electrostatic
me.
fields.
You haven't explained to me why 3 electrons has 3 times as much force as the 1 electron. That's what I'm asking you.
Well, they would have three times as much.
And how is it? How can that relate that in your binary space? Because at some point when you
remember
measure
the M-type bits.
It's not 1 or 0. It's 3.
Okay. So you've got 3 in a close vicinity of negative M bits. Okay. Well, that's increased negative charge density in that volume because they're right close to each other. The scalar bit operation, which means electrostatic bit operation, will tend to separate charge, and off they go.
Well, that explains why the 3 electrons might want to get away from each other. But assuming that they're there and you're observing 10 centimeters away, that doesn't explain the force that's 10 centimeters away.
It does, because if you're 10 centimeters away, those 3 electrons have to communicate the separation events that occur due to the scalar bit operation at the speed of light to the 10 centimeter away location.
So how does the electron 10 centimeters away know to be repelled with 3 times the force? I guess you're just saying that they individually do it.
Well, there's a greater likelihood that negatively charged M bits will become adjacent to the negatively charged M bits at the location 10 centimeters away after a delay, taking into account the speed of light. And then an electrostatic force will be exerted on that 10 centimeter away negative charge. I don't.
Once again, my only criticism is that you're saying Coulomb's law works because Coulomb laws work. It's fundamental in the laws of your system to do that, and that's okay. That's one way to do it. I mean, it's in the programming of your system that they will move apart. That's
the postulate of the first principle is the scalar electrostatic bit operation, which shows how like charges tend to be separated that are adjacent to each other. Okay. The Coulomb's law comes in my derivation of elementary charge. That's where it comes in. You could read the original paper on binary mechanics. I don't even think Coulomb's law is even mentioned. It's not necessary. It is necessary in my particular derivation of elementary charge. I just put a video about that on BitChute and binary mechanics lab separated by underscore characters where the spaces are, a little advertisement, excuse me, on how it was derived. That's where the Coulomb force comes in. But as far as binary mechanics goes, if you're not deriving fundamental constants like elementary charge, Coulomb's law is not required. What's required is the scalar bit operation and the binary mechanical concept of physical space or model of physical space.
all right. Well, I would. Well, I think we know what the differences between our theories are, though. Okay. So let's see. So you're trying to make a tri-state computer. So I think I've just asserted that it's more than a tri-state computer, that my space loci must have a property that actually represents what would be called pressure. And there would be pieces of code in my system saying that if there is higher pressure, then that is the code is designed to say those things move apart from higher pressure.
Okay. If I may,
pressure
I don't want to appear to be argumentative because, in fact, I think your train of thought is extremely similar to what's developed in my work. When you say the pressure, as far as I'm concerned, that's just a code word for saying the scalar bit operation.
It could be, maybe.
I mean, it's the same thing. You said there's a pressure that tends to separate charge. Well, that's what the scalar bit operation does, demonstrably.
Now, I'm only attracted to that because I know of some experiments where this has been physically demonstrated with balloons pulsing inside of water. Because, once again, it's very hard to get this kind of observed force generated between things which aren't necessarily connected to each other it looks like action at a distance, right? It's kind of hard to get two things to collide into each other. But in that case, the reason, he has these pulsing balloons in water, and if you pulse them at the right frequency and phase, they will actually get pushed towards each other. So that's why I'm attracted to this concept, and it's more intuitive. And I try and I'm more of an intuitive, mechanical thinker, so my thinking tends to go in that direction. That may be right or wrong, but I'm thinking that the only reason why two things would be repelled to each other or be attracted to each other is due to, say, Newtonian type collisions. And those Newtonian type collisions are mediated by particle waves, kind of thing. But still a work in progress. I mean, ultimately, I still like the idea that God just invented the electron and how it worked. And once you do that, then everything else comes out of it. For example, the only difference between the electron and positron in my model is that there's a phase difference, right? So in a binary computer, you only have two choices for a bit to be in any given slice of time, right? So that would correspond to what the positron and the electron is, that they can only be in one of those two binary states. And they're physically the same thing, still represented by exactly the same physical memory cell. It's just that when you started up the computer, it's like randomly half of them are going to be zeros and randomly half of them are going to be ones. And that would cause the generation of the positron and electron basically C in the initial generation startup of the universe. And once it started, then they would have to remain locked as positron or would have to remain locked as electron. And they would be running at the opposite phases, and the only rule in my piece of code in my system says that once they start going at that 1 and 0, then they start sending out a wave out into space, into the space loci, representing the electromagnetic field pressure of 1s and 0s. So you would see that series of waves, and that when two waves intersect each other, like when you have like 3 electrons right next close to each other, then you would see that the pressures would add. And so you could physically measure, you looked at that particular cell, you would see that the value of pressure is 3, and it's a positron because of its phase, or it's an electron because of its phase. And then if you put another electron next to that, then just programmatically you would know that it's going to create this type of either repelling or attracting force.
Are you saying that the 0 state in a cube of space is a positron?
Well, in certain ways, yes. I mean, the loci that I have would in addition to having the pressure attribute, would have to have the phase attribute, and that phase attribute could only be a 1 or a 0. So that could be a binary value, versus the pressure, which would have to be some finite variable value.
Okay. This is why I suggested that in my email to you that basically, I think to carry your ideas forward, you need to write a computer program to simulate what you're saying in words. and actually show us that these events occur the way you're saying that they would occur.
Yes, that goes back to your first point, yes, which was I should write a computer program to show that this can actually be made to work hands off using actual code. Not an unreasonable idea to do. So let's see here. So let's see. So yeah, so I'm trying to build more than a tri-state computer. So certainly I could convert my definition to binary. Like I said, I could write a computer program where I define an XYZ coordinate space, and within each one of those things have at least a phase and a magnitude value in it. Those are the two minimum things I need to make my system work, and then show that I could put an electron over here, another electron over there, and that they would spontaneously fly away from each other versus a positron electron, and so they would spontaneously come together with relatively little computer programming going on with that, I suppose. But I suppose the most attractive thing about the simulation hypothesis is that I have not been able to come up with any reasonable model for what an electron actually is. I mean, other people do. Like last week, Dr. Lucas explained, he thinks it's a torus and things like that. And I just don't. It's very difficult to, and people will ask you, well, if an electron is fundamental, then, what's the electron made out of? And I can only say it's the electron. But if you accept simulation hypothesis, then ultimately the answer to what an electron is that it's just a bit state in the computer, right? That's what it physically is. It's just a bit state in the computer.
Okay,
and
well,
anything
Bill Lucas's model of the solitron is extremely similar to my model of space, which includes the electron spot, where three partial charges of 1/3 m bits circulate around a central axis.
Yeah, so you might be attracted to that. Me personally, I think if that were the case, then we should be able to see fractional charges maybe, but we never have. So, and there's no evidence that an electron is made out of 3 of anything. So I'm pretty sure that if that were the case, we would have seen it by now. Now it could be just that we have our limitations in our experimental setup, and we just can't, we just haven't been able to knock them apart. Or
okay, I'm not an expert on this experimental literature, but my understanding from reading different things around, that there is experimental evidence for fractional charge in contrast to what you just said.
I'm just not convinced. I mean, it's the evidence for quarks that they would be talking about. See, if quarks exist, then the fractional charges would have to exist. And the evidence for quarks is that, they collide things together, and, sometimes you see 3 things kind of being reflected out, not quarks, but, you could kind of presume that maybe there's 3 things coming out because there are 3 things inside of there, or it could just be that if you look at the clouds long enough, you can see anything, right? Me personally, I think a lot of that accelerator experiments is like winning the lottery. It's just like, if I run the lottery like 1 billion times, I will win, right? I will totally win, right? Does that mean I know how to win the lottery? No. It just means that if you run anything long enough, you'll see anything you want, right? I'm waiting for them to find the Mickey Mouse particle where the pattern is like 2 years and ahead, and call that the Mickey Mouse particle. You could find that, I'm sure, if you look long enough. So you can find anything, but I would say that the vast majority of the evidence is that the electron is fundamental. This is one of the things I've been arguing in my email quite strongly, because some people want to say the electron's made out of waves somehow, electrons are made out of tension somehow, but I just disagree with that. I believe that the best way to start is to start with things that we do know exist. We do know the electron and the positron exist. We do know their properties. So I may not know what an electron is, But if I build the entire world out of just electrons and positrons, that would be perfectly valid. But there's still this question of what is the electron? And that's where I like the simulation hypothesis, where I can ultimately explain that the electron is just a bit of state and a bit of programming code represented in the simulation. And that's what it ultimately is. It doesn't ultimately has no physicality to it. So that's one way to get around, you know, what the electron is. If you can just say it's in the computer. It's what, you know.
When you say, dear Franklin, it has no physicality to it,
it's not made out of a substance. There's no physical substance. It's although the computer is to be made out of physical substance, it's that couldn't be said to be the substance of the electron. The electron itself is defined by state and the programming around it. It's not anything tangible.
Okay, what you just said is binary mechanic type talk, and I applaud you.
Yeah, like I said, that part I think we totally have in
the
common.
binary mechanical model of space, which can have 1 or 0 bits in 6 out of 8 possible cubes in a cubic lattice, and the computer code are the bit operations, which say how this data is processed. That's what the bit operations are. As far as we're concerned, whether or not they're physical or not is a matter of philosophy. For physicists, the question is, what is the mathematics which explains heuristically the most possible phenomena?
Yeah, but I think this points out kind of difference, because you do have all these bit operators and you have your spot thing, and that compared to I would be interesting to, like, if I wrote my program, I would say that it would probably take less than 10 lines of code to describe just the basic attraction repelling properties using just the phase and the pressure magnitude attributes in there. So, you know, that would be an interesting exercise, just to see if I could create just a simple thing, because that is a much simpler picture than what you would be proposing, I would think.
Well, in one approach to developing a model of space-time energy quantization, which I actually presented here two weeks ago, or was it 3, was to take the complex amplitude used in the wave function in quantum theory and parse it. And I come up with a spatial object called the spot unit, which has 2 types of bits: the M bit, which has a charge property, plus and minus, and the L bit, which has a direction property, right or left, or depending upon which of the X, Y, and Z axes it is oriented on. Now, in other words, from really what we might call extreme effort of quantization, make things as simple as possible, I come up with 2 kinds of bits. You just said, dear Franklin, that in your spatial cube, you have 2 properties. What was it? The electron and the pressure.
It's phase. Phase is either 0 or 1.
See? So you see how close we are in overall mindset. I come up with 2 properties out of the complex amplitude of quantum theory, and in your thinking, you come up with 2 properties associated with a physical location. Also, I call mine the spot unit. You call yours just a cube. My spot unit actually contains 2 little cubes.
Yeah, my spot, I mean, that's a big difference, I suppose, that programming-wise, I only have to consider a single spot with 2 properties. And programming-wise, I only have to consider that that thing is changing in space from 0 to 1, so that has to be kept track. But additionally, I have to say that in the space in the cubes outside, that those are also taking on different pressure waves as I go out. So that's how I count for.
Well, you have to take into account, it seems to me like you just broke the conservation of energy law, and if you wish to do that, fine and well. But in binary mechanics, one-state bits are conserved. They're never destroyed. They either stay where they are or they move somewhere.
Bits are never destroyed. They're either 1 or 0. Although that does bring up the interesting question.
Well, if a wave is going out, what is the wave? It's some kind of a bit, isn't it? So where did that bit come from?
It just comes from the programming that says get it from the previous block. Depending, I guess also.
So you're saying the previous block will no longer have pressure
property as well.
So you're saying the pressure property moves, and the block or cube that it moved from now has lacks that property.
Yes. You just like a shift register, it would just shift the bit out.
I call that the unconditional bit operation. You see how similar our thought pattern is.
Yeah, like I said, I think it's similar.
I'm encouraged. I am vastly encouraged to hear your thoughts. Yes.
But I'm kind of working this out myself because, like I said, if I were to make a computer program, how much code would it take for me to encode just the electron? Because that's what I assert. I assert that if you encode the electron, I think that's what God did. Then once he did that, then the rest of the universe fell into place, including atoms and everything else we have, gravity, magnetism, basically all fall into place, since my grand scheme is that you have the positron, you have the electron, and that just randomly fills up all of space. But together, the positron and electron are effectively a neutron. So effectively, all of space is filled with neutrons. And
in my email to you, Franklin, I mentioned that you might want to write such a program because writing the program requires precision definition of everything you just got through saying.
Yes, exactly.
And you're going to see what issues there are and are not. Because once the program is written, there is no more flowery talk, okay? About this is a pressure and blah, blah, blah. It's has to be defined unambiguously. And so that's what I think listeners to your point of view, which is so close to mine, but perhaps with differences, as you say, need to see. They need to see you taking, not just saying, well, we have this rule or that rule. What exactly are the rules? And you'd have to be very exact to program it. Program it and let us see your wave of pressure or whatever move across the screen and so forth.
Yeah, like you said, that would probably be a good thing for me to do if I'm really serious about working this out. That would be interesting, but I'm just, and it would show either how complex or how simple it could be. So certainly in my case, my individual space locations are more complex. I've identified at least 3 things now that I would have to have. It has to have the phase 0 or 1, has to have magnitude from 0 to whatever, and also it would have to have a vector direction so that it knows where to shift that bit, right? Because if it's going out this way, it needs to go that way. If it's going this way, it needs to go that way. So there would have to be something that has at least a binary thing, because I'm thinking that basically you have the electron sitting in space, and when it switches states, like the 1, then it has to send that state around in, first of all, it's like a Rubik's Cube. It would go in the center, it'd be like Rubik's Cube side, a 3x3 object, and then a 4x4 object, and then a 5x5 object. And
where does all that energy come from? Like you have to conserve energy. But what you just said about the 3 properties of direction, phase, and what was the other? Yeah,
magnitude.
The charge.
Yeah.
It sounded like if nobody knew, they would think you're describing the spot unit. It has direction.
Well, it could be.
When M bits
fundamentally,
are shifted in the unconditional bit operation, they become L bits within a spot unit, and that can be viewed as a time phase shift.
But how would you represent the vector component?
The what component?
The vector component.
Oh, those are the L bits. In fact, the L bits, in recent papers, I've mentioned the possibility that some or all L bits are in fact equivalent to the discovery of a magnetic monopole. In fact, there's a paper on proton and electron motion after injection of a magnetic pulse by injecting L bits, okay, in a certain direction in, say, 1/2 the volume. And what's the effect? Both positive and negative bits in the positive electron bit cycle and the positive proton bit cycle and the negative electron bit cycle move in the same direction, just like with a magnet, okay?
Well, I'm not sure I understood actually any of what you just said. I mean, just to be honest, that was like word salad going right over my head.
Well, we've been talking about the charge, the M bits. What about the L bits? That is your magnetic field. The L bits are the magnetic field. You see, in classical physics, which I know you sort of reject,
magnetic field. That's just like going. It's just like that doesn't say anything to me.
Well, in all the physics books, that the last time I checked, they talk about electric fields and magnetic fields. That's all I'm saying, and I'm saying that the physical substrate of the electrostatic field are the M bits and their distribution within a volume. The physical representation or substrate for the magnetic field is the L bits. And if you look at the L bits, they either have a right or a left direction. In other words, they're magnetic monopoles.
Well, in your simulation, have you gotten an electron to deflect in your theoretical magnetic field?
Yes, and they deflect in the same direction as the positively charged particles, which is what magnetic fields do. In electrostatic fields, the positive and negative particles deflect in opposite direction according to the gradient of the field. And so there are two papers
about magnetic fields
that kind of motion.
Is that they deflect opposite charges in opposite directions at all times, right? If you got it,
well, in an electric field, they would, yes. In a magnetic field, they both, according to my data, deflect in the same direction. Now, the amount of deflection might vary. The amount of deflection of the bits in the proton bit cycle may vary compared to the electron bit cycle elements.
Did you not hear me? I mean, that's empirically wrong.
Excuse me?
Clearly, in a consistent magnetic field, you see pictures of this in cloud chambers, that positron curves right, electron curves left. They definitely go in opposite directions through a uniform magnetic field. That's empirically Lorentz force law. If the sign of the charge changes, the force must change, right? If you weren't aware of that, I mean, that's a big problem because the charges have to go in opposite directions in a magnetic field. You might want to check that.
Well, you're saying in a magnetic field.
Yes, in a magnetic field.
The magnetic field in my work would push both in the same direction.
Yeah, and I'm saying
if there's an electrostatic field,
that is wrong. Empirically, that is wrong. If you weren't aware of that, I mean, it doesn't matter what your theory says. I mean, if your theory
I'm just saying the data of a simulation experiment. My theory doesn't say anything one way or another about that, so we're okay there. But in a simulation experiment, I have shown by injecting a magnetic pulse. Now you're talking about a steady magnetic field, but injecting a magnetic pulse right at the beginning of the simulation. Both the plus and minus charges move in the same direction. The amount of displacement due to the pulse is different, okay, because they have a different mass, but the direction is the same. Okay.
Well, I would study.
In other words, if you put a magnet up to a piece of metal, let's say you can polarize the electrons and protons within the metal, but depending upon the pole of the magnet, you can either attract that metal or perhaps repulse it. Am I making sense here? Maybe I'm not.
Well, no, I mean, it just sounds like you have a major misconception about how the magnetic field works, and that you think that charges going through a magnetic field would go in the same direction. It would be insensitive.
Well, the experiment that I did was a magnetic pulse. There's no
I'm
magnetic field
by magnetic pulse, but you should be able to emulate magnetic field, a constant magnetic field, because that's what Lorentz force law is based upon.
Oh, I'll try doing that experiment. I'll think about. I haven't done that experiment
about that, because you have to get the result that the electron goes in the opposite direction under those conditions. So,
under those conditions, I'm sure I would see a polarization, which indicates that yes, the charges have different trajectories. But I haven't done that experiment. I haven't done it yet.
That's an interesting.
You can download my simulator and set it up and do it, and see.
And the other thing you have to simulate is that once you've got that magnetic field set up, if you put an electron in that field, it's got to be motionless. Zero forces have to be exerted on that thing. That's the other hard thing about the magnetic field, is that it can't be any kind of flow, because if you put the electric charge in that strong magnetic field, it feels zero force, zero, right? So it can't be due to any motion or any net attraction. The only time it feels any force is if it's in motion relative to the magnetic field. That's the other thing that's just hard to replicate.
Well, that was a great opportunity for the participants here. Download the simulator and set up the experiment. I haven't done that experiment, so I can't comment one way or another what would happen.
Okay, well, it seems like we are at the end of our time. So we had started out with Aberchecki bringing up his question about the bucket of water with the duck in it, and eventually, Carl came up with another analogy where you have the train full of water where you can observe the waves. I think that made a little bit clearer as to what we would be able to observe on the outside of the train. I guess at least my conclusion was that you would just see a shifted increase in frequency, that the Doppler effect probably really doesn't necessarily apply to the situation where the waves are not allowed to escape the moving object. So you're the passenger in the train, or you're just waves in the train, I guess. But that was a little bit more complicated than I thought, a little more interesting. It's a little bit more, goes beyond just basic what is Doppler and what that works. And then the second part, we were discussing the email between me and James about our models. So we both agree that there could be this computer behind it. Now mine is a little bit, I think we established that mine is a little bit more complicated, and it's actually more than tri-state. Actually, each of my bits has to be able to hold at least 3 properties, which is a phase, which I relate to being a positron or electron, and that defines what positrons and electrons are, and a magnitude of pressure, and a directional vector that could point in any spherical 360-degree direction, so that any effect that's propagating away from the electron at the center knows where it goes. And so that's at least helped me to kind of codify that. And James has said that, you need writer programs so you can see what's going on. And it's like, Yeah, the computer programmer, I probably should. That'd be an interesting exercise. Anyways. So, but that will do it for this week's episode of Science Chat. So we are kind of changing the format a little bit of the Science Chat, that if we don't have specific topics, then maybe we won't have a Science Chat that week, or maybe I'll just, like the one week, I'll open it up and you guys can just talk amongst yourselves if you have a topic that you have. But it'll be kind of a no-host thing. But I'll try and make an announcement one way or the other. And if anyone listening has got a topic they would like to speak on, so James, if you would like to, I know you've got a lot of different stuff. We only just kind of got to the tip of the iceberg, really, with your stuff. If you would like to present on some of your other ideas, I would invite you to do that. So just let me know ahead of time so we can all know that you're doing that. Okay? All right, but that will do it for today. Thanks for everyone for participating.